For our final installment in Chapter 9, we're going to use kinetic molecular theory to explain a lot of the observations that we've encountered in this chapter, and then finish by looking at non-ideal gases. So let's dive into it. Kinetic molecular theory, which is section 9.5. Okay. We have used the ideal gas law, which we saw came from a number of experiments, right? We experimentally had determined Boyle's law, Charles' law, Amundsen's law, Avogadro's law. Those were determined in the lab, right? But they don't explain why gases follow these behaviors. Okay, kinetic molecular theory, or KMT, does. It's a microscopic model, and it follows 5 postulates that we'll list on the next 2 slides. And one thing just to have in the back of your mind is, while it's called kinetic molecular theory, it applies to any type of gas, right? It could be an atomic gas if we had a noble gas, for example, okay, something like helium. So what are the 5 postulates of kinetic molecular theory? Number 1 tells us that gases are composed of molecules that are in continuous motion, which you probably already knew, right? Gas molecules aren't just hanging out there in place. And these gas molecules travel in straight lines until they encounter something, either another molecule or the walls of the container, which we've talked about previously, right? They're bouncing around until they hit another gas molecule or the wall, and then they bounce back off. We consider the molecules or atoms of the gas to be negligibly small compared to the distances between them, right? So we've got these tiny little particles floating through vast distances before encountering anything else. Okay. And as we mentioned in the very first video, right, the pressure that's exerted by a gas in any container results from the numerous collisions between the gas molecules and the container walls. None of those individual collisions is notable, right, but the sum of them all gives us pressure. Postulates 4 and 5. Okay. 4 says that our ideal gas molecules exert no attractive or repulsive forces on one another or the container walls. They don't have any other interaction than would 2 marbles hitting each other, right? We consider the collisions to be elastic. They don't involve any loss of energy. So these things are not attracted to one another. They don't repel one another. And lastly, the average kinetic energy of the gas molecules is proportional to the Kelvin temperature, which we've seen before when we were looking at pressure. Okay? And we know that idea with kinetic energy from back in chapter 5. As we increase the kinetic energy, we increase the temperature. Right? Now our gas molecules are moving around faster. So what's that look like as a picture? Okay, well, if I heat something, looking at A, things start to move around faster. Okay, that gives us higher pressure, right? Boyle's law, B there. If I decrease the volume, I have more collisions, right? So as volume goes down, pressure goes up. And then Avogadro's law, C, right? If I increase the gas, I have more collisions, right? And so they take up more space. All of the laws can be explained with kinetic molecular theory, right? So there's a lot of text on these 2 slides, 78 and 79. The numbers might be slightly different in the slides that you have, but take time and read over them. The question on the top of the slide is, does it work? Well, yes, because we've already sprinkled in a lot of the ideas from kinetic molecular theory when we were introducing these ideas in the earlier videos. Next, we have the idea of molecular velocities, thinking about these particles that are moving around. Because in a sample of a gas, the molecules that are in there vary in speed quite a bit. Not every gas molecule is moving around at the same speed. Okay? But because we have such a large distribution of numbers, just like you have a distribution of grades in a class, right? We have the molecular speed distribution and average speed that end up working out to be constant values. So they're kind of a representative of the sample. And that distribution of molecular speed is known as the Maxwell-Boltzmann distribution. And as we've kind of alluded to already, it depicts the relative number of molecules in a bulk sample of gas with a given speed. So what do they look like on a graph? Okay, we've got, right, 2 points here, our velocity and our most probable speed, right? Root mean square speed right here, right? Most probable speed and root mean square speed. So what do those look like, right? Kinetic energy and root mean square speed. It is measured by this equation, right? And your textbook goes into the derivation of the equation. You don't have to know. This won't be on a quiz or a test. You'll use it on one of your sapling questions, okay? U is the root mean square speed, root mean square velocity. And that's equal to the square root of 3, number 3, times r times t over m. And this is tricky because this r here in the root mean square calculation is a different r value because we're dealing with energy. Okay? In Chem 2, we'll see those r values jump back and forth. When we're dealing with pressures, we use our earlier r, 0.08206. Okay? But here, when we're dealing with energy, this r term is 8.314 joules in the numerator, right, the unit for energy, and the denominator is mole time Kelvin, which means that T here, our temperature, has to be in Kelvin, and M on the bottom is the molar mass. So if we look at graphs of these speeds, we see that an increase in temperature increases the root mean square speed. So you should know that. Maybe you already did. But also be familiar that as we increase the temperature, we increase the average speed, the root mean square speed, but we also increase the distribution. Notice how the peak of the curves is moving up, but the curves are also getting flatter. Okay, so the distribution increases as the average also increases. We see that by increasing the temperature or by decreasing the molar mass. Both of those are important. Know those ideas. Increase the temperature or decrease the molar mass. Both of those will increase the average speed and increase the distribution. So that wraps up 9.5. We finished the chapter with 9.6, looking at non-ideal gas behavior. Everything previously in this chapter was using an ideal gas. But we mentioned the limitations of that at the beginning. Okay? Rarely are gases perfectly ideal. Okay? So if nothing's perfectly ideal, the ideal gas law doesn't do the best possible job of describing it. And in fact, we can only truly use the ideal gas law to get perfect answers if we have a compressibility factor of 1. Okay? And the compressibility factor, Z, you see the calculation there on the bottom, it's equal to the molar volume of the gas at temperature and pressure versus the molar volume of an ideal gas. So if we're thinking about standard temperature and pressure, right, we know that the molar volume of an ideal gas is 22.4, the standard molar volume. So if our true gas that we're dealing with is anything but 22.4, then Z is not equal to 1. That means it's not ideal. And we can see for every gas, right, there's a certain pressure where we behave ideally and temperature, but chances are we're not. Okay? We use the ideal gas law for convenience, and that's okay. You'll continue to use it in your calculations. But why do we see gases not behave ideally? Okay? Well, if we think about some of the assumptions that we made in kinetic molecular theory, right, we were thinking about the fact that this hypothetical construct, this ideal gas, had particles that occupied no significant volume and had no interactions with one another. And in the real world, that's not the case. Okay? In the real world, gases can approximate that ideal behavior only at low pressure and high temperature, which you should absolutely know. For a gas to be most ideal, it needs to be at low pressure and high temperature. If we aren't there, right, if we are at high pressure, that pushes all of our gas molecules closer together. Okay? So what that means is that they are occupying more space. Okay? Our gas becomes less compressible. Okay? They're taking up a higher percentage of the space. What else is going on? Okay? Well, and we'll talk about intermolecular forces in Chem 2. Right? But if I push my molecules closer together by increasing the pressure, right, then all of a sudden, right, they can start to interact with one another more. Okay? The force of attraction is no longer insignificant. Okay, so that causes change to our pressure. And that can be affected by the temperature as well. Okay? If I cool a gas down or if I increase the pressure, right, they start to interact with one another to a higher degree. So this is known as the van der Waals equation and the non-ideal gas equation. What's on here over to the right? Okay. The ideal gas law is PV equals nRT. Okay. With a real gas, we have to make a correction for the molecular attraction we just talked about and the volume that they occupy. So we still see P and V again, right? And N is moles, but then we have these A and B terms that are unique to every gas. So you're not going to be ever asked to use this non-ideal gas equation, but you should know the conditions where we have deviations from the ideal activity. Okay? Because using that equation is a pain. We always want to be able to assume that we have an ideal gas. But what you should absolutely know from section 9.6 is, sorry, I'm skipping this one. All right, under what conditions would a gas have the most ideal activity? Low pressure, high temperature. Know that for sure. Know the conceptual ideas from kinetic molecular theory from video 5.